Okay, welcome. We will continue our discussion on generative models. So, last time we looked at the general principle of what generative models are and looked at an example of adversarial networks as generative models. So, today I will continue that discussion and introduce you to some more, rather couple of more ways to look at generative modeling. One model that I wanted to talk about is latent variable generative models. Of which variational autoencoders is a member. That's a large family of generative models. In fact, diffusion models or diffusion probabilistic models are also called denoising diffusion probabilistic models, right, DDPMs. So, they are also a member of this family. Flow based models, okay, normalized flows are also latent variable generative models and so on. But in this course we will only looking at an introduction of what a latent variable generative model is and give one example of it, which is VAE. I will also talk about the autoregressive generative models of which the LLMs, large language models, are a family or a member, and all the AI chatbots and the LLMs that you see today are autoregressive language models, autoregressive generative models. So, we look at examples for these two families. So, we already saw what a latent variable model is, right. We start with data which are n draws from an unknown distribution. So, the goal is to sample so estimate Px and sample from it. We saw the general principle in the last class, right, where you start from an arbitrary random variable that you know how to sample from and then learn a deterministic function on top of it and tweak the parameters of the function such that a divergence measure is minimized. So, that sampling from an arbitrary random variable and doing a function approximation, rather passing that sample from an arbitrary random variable to this deterministic function will finally yield a sample from the distribution of interest, and we saw how to do it using adversarial learning. Now, in latent variable models, recall what the model is, right. P theta of x in a latent variable model is the marginal of the joint distribution. You assume that there exists a hidden or an unobserved random variable called the latent variable, and you express the marginal of the data as an integral or a sum over the joint distribution of the data and the random variable, the latent variable. Now, by construction, so what a latent variable model gives you is that it will, a latent variable model imbibes generative property by construction. So, what do I mean by that? So, a latent variable model, once you fit a latent variable model to a particular data, you can estimate distributions such as p theta of z given x, right, and p theta of x given z and p theta of x. So, now this is the embedding extraction. See, once you have a latent variable model, given a data point, if we estimate the posterior of the latent variable given data, that becomes a feature on embedding. We already saw examples for this, right. If x is discrete, then clustering is exactly this, okay. So, I did not talk of this particular distribution yet, right, which is the distribution of the data given latent variable. If we can sample from this distribution, this is sampling. I can say this as conditional sampling, conditioned on a latent variable model, latent variable value z, I can now sample from p x. So, this becomes a sampler. Now, a latent variable model, if you fit it right, then it can serve both as an embedding extractor and a generative model. Okay. This did not happen with adversarial networks for instance, right. So, it can sample from the distribution, but given a particular data point it cannot give you embeddings, right. But a latent variable generative model can do both. It can given a data point, it can give you the embedding. Given a sample from the latent space, it can generate a new data point. Okay. Now, we already have seen an example for this. So, in this sense, what can be seen is a latent variable model can be seen in this light. What it typically does is starts from the data space and learns a projection to the latent space, and from the latent space it gets back to the data space. Okay. So, this is p theta of x given z, and this is p theta of z given x. Sorry, it is the other way around. Yeah, it is the other way around. So, yeah, given x it will give you a z, given z this will give you an x. Hold on, right. So, typically this is called the encoder and this is called the decoder. Starting from the data space, you project to the latent space is the encoder function. Encoder function from a probabilistic standpoint is the estimator of this posterior of the latent variable given data. The decoder function is always the estimator of the distribution of data given the latent variable. So, these are latent variable models are therefore encoder decoder models. Okay. Questions? You had a question on this? Yeah.
In general, a question about the latent space distribution. So, every embedding we have, we are projecting the data onto another space, is what you do. So, in that case, the distribution of the data is itself changing, as you mentioned in the previous.
Of course, yeah.
So, aren't we getting the embeddings which have a different distribution than from the data itself?
That's okay, no? Yeah, that is correct. The distribution of the embeddings is given by p theta of z given x. So, it is a different distribution than data. See, as long as the clustering properties, okay, of the data is preserved in the embedding space, we are okay, right. So, the question that you asked is actually pretty profound in the sense that all the latent variable generative models ask this question. So, what should be the ideal latent space that is to be embedded, so that desirable properties are imbibed onto the latent space is a question that is to be asked. However, as long as the separation of the data, or rather distribution of data, not in the probabilistic sense, right, in the suppose you are looking at a classification problem, as long as and it's a 10 class classification problem, as long as those 10 classes gets clustered in the latent space as well, we are okay about what the distribution of the latent space is, right. Is the general way to look at it, but the question is very valid. So, what should be the latent space? See, that translates to how should I learn the embeddings, right? What should be the underlying model itself, right? That is the modeling question. Okay. We will see one example of that, which is the variational autoencoder right now, where a specific type of distribution is imposed on the latent space for a particular reason. Okay. We will see that, but this is what in general a latent variable model does. Now, if we, as I said, if we learn it well, then the decoder of the latent variable, okay, so the model, so the encoder is the feature extractor, and decoder is always the sampler or generator. This is the general convention. Always the encoder is feature extractor and the decoder is the sampler. And the autoregressive models that we see later are decoder only models. Even GAN for that matter is a decoder only model, because you only have the sampling part, not the embedding extraction part. You understand? So, that is the nomenclature. There are encoder decoder models, there are encoder only models. See, all the NCE based models are encoder only models. Why? Because ultimately what you get is a feature. So, you are getting the Z, you are learning a transformation from the data space to the latent space, not the other way around. So, there are encoder only models, okay, and there are encoder decoder models which will give you both the embedding and the generation. and there are decoder only models which are only designed for generation but no embedding extraction. So, we have seen all kinds of models in this course. GAN is a decoder only model, it is only a sampler, and the self supervised learning, SimCLR, etc. are only encoder only models, and there are encoder decoder models as well, and so on. Okay. Now, let us look at an example of a latent variable model being a generative model, right. So, example of latent variable models. Latent variable generative models we will see. I want to talk about two examples. The first one is something that we have already seen, which is the Gaussian mixture model. So, GMM is the simplest of latent variable models, that is also a generative model. We never saw GMM as a generative model so far, correct? But since it is a latent variable model, it should be generative as well. So, we will see how to use this as a generative model. So, we know that in a GMM what we do is we model p theta of x as the marginal, the latent variable is discrete here, and what is p theta of x given z? It is p theta of x, sorry, p theta of x and z is p theta of x given z times p theta of z, and this is in a GMM, this is a normal distribution, right. So, which a particular mean. We have some alpha c here. This is what the model is, right. So, we know how to fit the model. Okay. So, I am using this word fitting the model, I mean I never use this word in this entire course, right. So, model fitting. So, what is it? It's ERM is what we are talking about, or the divergence minimization is what we are talking about. So, once we have a GMM that is there, we have a p theta. Okay. So, post ERM or post ML estimation, theta star would be known. What is theta star? Theta star in this case would be set of alphas from J1 to capital M if there are M mixtures here, and we have M mu's and M sigmas, right. Given data we know how to get these. So, we have gotten this. So, now how do we use this for generation? So, for generative inference, this is how we do it. First thing is sample z from p theta star z, okay, then sample x conditionally from p theta star x given z. Let me call this z cap. So, given this z cap, I will have to sample from p theta star x given z cap. That is it. So, now this becomes a generative model. Let me give an example, or rather walk you through an example. Let us say that we are having MNIST data, okay, no labels. Take all MNIST data and fit a GMM to it. Okay. So, you choose how many components do you want, that is a hyperparameter, you fit a GMM, okay, using EM. Now, once you have the parameters, what you should do is that you need to first sample z from p theta of z star. What do you mean by sampling z cap from p theta of z star? What sort of a distribution p theta star of z has? Yeah, it is a generalized discrete distribution, right, whatever we had done earlier, remember it is throwing a die, this is throwing an M phase die, right. So, do we know how to sample from this? We know how to sample from uniform distributions. Do we know how to sample from a discrete distribution of any given probability mass function? Please take it as a homework and do it. Here is the question. So, it is one of the favorite interview questions in ML interviews, right. So, given that you know how to sample from uniform distribution, okay, give me an algorithm to sample from a discrete distribution of given probabilities. I will give you P1 through Pm, that is what we have given, right. Once we estimate these alphas, what are alphas? Alphas are nothing but the probabilities of this discrete distribution. So, given that we know how to sample from this discrete, so we know how to sample from a uniform discrete random variable, give me an algorithm to sample from any discrete distribution with given probabilities. Is it? Okay. So, do it. What is more interesting is you can actually make it an algorithm question and try to make it logarithm complexity. So, do a brute force and see what the complexity is, and then you can make it faster as well. Okay. The hint is you use inverse CDF method. Yeah. So, you should use the inverse CDF method that we discussed the last time, that is how you do it. Okay. Now, we know how to sample from a discrete random variable, right. Once we do it, if we do that, what do we get in a GM, in the context of GMM? If we sample from this discrete distribution, what we get is a component. So, once we sample, we get one of the m values. Once we get one of those m values, the underlying Gaussian distribution gets fixed. No, a GMM has m Gaussian distributions, a mixture of m Gaussian distributions. So, once you get one value for z, one of the m's get fixed, then you just sample from a Gaussian distribution, that is it. So, this sampling will give you a point in d dimension, which is an image, right. In fact, in one of your assignments, right, I would ask you to just split a GMM to some data set and then sample. If you do that, you should get an image, right, a new image that is not there in the data set. That is it. This is as simple as it gets, and this is how you use GMM for sampling. Finally, sampling from a GMM amounts to sampling from a Gaussian distribution. But before you, there are m Gaussian distributions. Before you choose what Gaussian distribution to sample from, you do a discrete, to decide what Gaussian distribution to sample from, you first sample from a discrete distribution, and then conditioned on that you sample from that particular Gaussian distribution, that is it. Yeah, that is how you use a GMM for sampling, and you can extend this for any mixture variable, mixture model, right. It need not be Gaussian mixtures, can be any mixture model where you have a discrete mixture, you sample from it and then sample from the underlying distribution, that is it. Okay. Now, let us move on. Now, the problem with a Gaussian mixture model is that recall how we did EM for this. When we did EM for this, we assume that we know the exact Q, the variational distribution that would make the elbow tight. What was that exact distribution? It was the posterior of latent given data, right. What if you have a model where the posterior of the latent given data is interactable? So, how do you solve a latent variable model? How do you fit a latent variable model to data in that particular case is the question. Okay. Now, notwithstanding the math, as I said, it is for the next course to do. This is exactly the question that is asked in what is called as a variational autoencoder. So, it deals with a latent variable model where the posterior of the latents given data is not tractable. See, what happened in a Gaussian mixture model or any mixture model with a known conditional density is that this was computable because we use Bayes rule, right. This was proportional to p theta of x given z times p of z, and p theta of x given z had a known form. So, we could get the posterior, that is what we do during a EM, is not it. But what if, I mean, that makes the model very restrictive, because you should only choose the known conditionals for the latent variable model. If you want to make it more general, what happens is the posterior will be unknown. So, when the posterior is unknown, what do you do is the question. Okay. Now VAE solves that question as follows. I will not go into the details. So what happens is, one thing to be done is, you recall we had a lower bound on the evidence. So that is what we start with. So the elbow, what did we call it, was f theta of q, right. So what can be shown is that you can create a you can express the elbow in this particular form, expectation of log of p theta of x given z. This distribution is with respect to q z given x minus the scale divergence between q z given x and p z. I will start my next course with deriving this particular equation, okay, that is what we start from. So now take it for granted, you can rewrite the elbow this way, it requires a little bit of algebra, but you can get there, right. So you can write it this way. Now note that this q of z given x, right, is the variational posterior, unknown variational posterior, okay. In the case of GMM, what happened was, this was exactly known. So what is the optimal value for this variational posterior is p theta of z given x. But if you do not know how to estimate this, what do you do is the question. So what VAE does is as follows. So in VAE, so p theta of x given z and q of z given x are represented using neural networks, represented using parametric functions, okay. In this case we use neural networks, okay. You express the conditional of data given latent and the variational posterior of latent given data both using neural networks. So what do you mean by representing a distribution using neural network? No, see, there are two ways to look at it, okay. Now suppose there is a neural network, okay, that is representing a particular distribution. So it takes, let us say that it takes x, and what we want to estimate is q of z given x. There are two ways to do it. One, you make this neural network, okay, output a sample of q of z given x. This is what we do in our classifiers. What does a classifier do? A classifier estimates p of y given x, right, takes an x and gives you a sample from p of y given. Actually it depends on what sort of design choice you will take, okay. Now I will tell you, one is that I will complete the classifier story in a while. See, one way to represent a distribution using neural network is that you design your neural network so that it gives you a sample of the distribution that you are trying to estimate, okay. The other way to do it is you design the neural network to output the parameters of the distribution that you are trying to estimate, okay. Now I will come back to the classifier question. So the classifier, suppose you have a k class classification problem, you have a softmax at the output, what is it giving you? Is it giving you a sample of y, or is it giving you the parameters of the distribution of p of y given x? It is giving you the parameters of distribution of p of y given x. Why is that? Because p of y given x is a discrete distribution that has probabilities p1 to whatever pk, if there are k number of classes, and it gives you an entire distribution, right. What do you do with that distribution? You sample from y, by taking the max or whatever, you have an entire distribution over y given a particular x. Do you see that, right? Suppose you put a let's say a max function on top of the softmax that you have, okay, then that neural network will give you a sample of y, not the distribution. Why? Because it gives you a one hot vector which is a sample of y. See, think of the neural network as it first gives you parameters of the distribution that you want to estimate, and then you have some sampling method that would give you the sample, that is it. So this max can be a sampler, that is it, okay. Now GAN, right, with the generator in a generative adversarial network, it approximates a distribution, right, it is estimating a distribution, representing a distribution. Does it give you parameters or samples? It is designed to give you samples, not the parameters of the distribution. You see what I am saying, right. So, in a VAE we estimate this distribution by estimating its parameters. So, what is assumed is you assume this q of z given x, okay, to be a Gaussian distribution or any parametric distribution for that matter, with some parameters mu phi and sigma phi, okay, and this neural network will give you two vectors which would serve as the parameters of the distribution that it is estimating. Do you see this, right? Then you have another neural network which is the decoder neural network that would estimate p theta of x given z. Now, what would this take as an input? It should take a sample of z as an input and should give you a sample of x. Either it can give you a sample from p theta of x given z, or it could give you a parameter of the distribution as well, that is also a design choice. So, this is the encoder of a VAE and this is the decoder of a VAE because of the reasons that we just saw, right. It is a latent variable model. Now, the question is, where do you get this z from? Huh? Exactly. So, what you should do is that you get your mu phi and sigma phi and then sample from this q of z given x, okay, and then give this sample as an input to the decoder. So, now there is a sampling process that is happening outside the neural network. So, the entire data flow looks like this: take a sample x, pass it through the encoder, get mu phi and sigma phi, use that to sample a z in the parametric distribution, take that sample, pass it through the decoder and get a sample of x. This is how the data flow happens in a VAE. Any questions on this?
So when you said use it to sample a z, what exactly do you mean?
You need, see, you want to sample from a Gaussian distribution, right? To sample from a Gaussian distribution, you need to know the parameters of the Gaussian distribution, which is the mean and variance. Where are you getting it from? From the encoder. So, every time you pass an x, you get a different mu and sigma. Use that mu and sigma and sample a point from a Gaussian distribution with that mu and sigma. We know how to sample from a Gaussian distribution, right? So, then pass that z sample to the decoder. That is how the data flow is.
So the conditional neural network give the mean of the distribution.
With mean of what distribution? Q of z given x.
Whichever distribution we assume on.
It depends upon how do you model it, that is a design choice. In the case of VAE, if you assume q of z given x to be a Gaussian distribution, then you can make the output of the encoder to be giving mean and variance of the distribution, that is it. Got it? Yeah?
How do we ensure that the model is giving mean and variance?
You do not ensure it. You let us say that you are operating your dimensions of z, okay, is k. Hold on, dimension of z is k, right? Then if you assume the variance to be diagonal, then you make the output of the neural network to have 2k dimensions. Take the first k dimension to be the mean, the next k dimension to be the variance.
Okay.
That is it. Design wise, that is how you do it. Now, what is the question?
So, my question was that what we intend is that at the end of the model we should get 2k parameters which represent the mean and variance of
That is enforced by design.
Okay.
Right. If the question is what loss function are you using, it is this. Still not told you how to optimize this loss function with this architecture. I will tell you that in a while. Okay, but question, yeah.
So when we are using this latent variable model for this feature extraction, will it not be advantageous to use it to give a sample from the distribution rather than the parameters itself?
Again, depends. Okay, the question is if we want to use a latent variable model for embedding extraction, why do you want to model an encoder as parameter modeler? Instead of that, you can make it a sampler, right? You can, right? But if you see, there are these models called adversarial autoencoders or even vector quantized VAEs, VQVAEs. So, VQVAEs do not give you parameters, they actually give you samples themselves. So, there are such models, but making it a parameter making it give parameters has its advantages, that sampling is easier that way. Okay. So, these are questions that we will actually address in the next course when we do it. Yeah.
Also, when we will use the decoder part for generation, so that time we have to sample it anyway.
Exactly. So, that is one other reason, that is why it said no, it enables sampling. So, what happens is if you make it give you samples rather than parameters, during inference if you want to get the data point, so you want to sample from the distribution that the latent space is learning. So, how do you do that? In a VQVAE, what is done is you fit another generative model on post hoc on that, on the latent distribution of latent space. That is one other additional step that you do. You can avoid it by doing it, is the idea. Okay, you can ignore that discussion. Did you understand what is happening architecturally? Right. Now, what should we do right now is that we will have to see, ultimately what we are trying to do is fit a latent variable model which is minimizing the KL divergence between p theta of x and px, that is our thing, right, our objective. And we showed that it cannot be done, it is not tractable, that is why we computed a lower bound on it, and this is how the lower bound looks like. Now, we have to optimize this particular loss function using this architecture is what we should do, right. Let us do that. Question? Yeah. Go on, go on.
If you assume that the latent is a Q Z given X is Gaussian,
Mm.
then sigma must be positive semi-definite.
Yes.
So even if we assume that sigma is diagonal, so we also have to additionally ensure that the output, like the last k output must be positive.
That you can do by you choosing the activation function. By putting appropriate activation functions at the output of this encoder, last k output of the encoders, you can do that. That is how it is enforced. See, any kind of output enforcement that you would do for a parametric neural network is done using activation functions, no? If you want it to be bounded between 0 and 1, put a softmax, or if you want it to be continuous, you put an R, then R plus, whatever the kind of activation function that you need at the last layer, you do it that way. Okay, so now the question is, this is the objective function to train this VAE. By the way, this is what is a variational autoencoder or a VAE. So, we have this f theta of q phi. See, note that this encoder neural network are parameterized by phi, and decoder network is parameterized by theta. So, we have two distribution, two parameters now, two set of parameters to be learned, q phi and p theta. Okay, now what should we do is we should find the derivative of this particular function elbow with respect to phi, and we will have to do it with respect to theta. Sorry. We need to do this, right, because ultimately we need to back propagate this particular loss through both the neural networks and do this. Now, look at what is happening. There is a problem with this. The problem is that this entire architecture has a sampling process in between, correct? How does that show up in math is that you are trying to find an expectation of some function with respect to a distribution, and this distribution, okay, is also parameterized by the same neural network, and there is a sampling that is coming here, and sampling is a non-differentiable operation. You cannot differentiate through a sampling process. See, if you look at the sampling as a black box, differentiating through sampling is not possible, right. What do you do is the question. To do that, the authors of VAE came up with this idea called the reparameterization trick. Where the idea is express this particular expectation in terms of an expectation over another arbitrary random variable that is not dependent on phi, g of epsilon, where G of epsilon is a function that takes an arbitrary random variable epsilon, which is normal 0 1, and then transforms it to G space. So, this is a known result in statistics. Okay, I will go to the details in the next course. The idea is that you can transform one random variable into the other via a deterministic function that we know, right. So, construct a deterministic function G such that the random variable with respect to which you need the expectation, which is QZ, okay, is represented using another arbitrary random variable that is not dependent on the parameters phi. Now, you remove the dependence on Z from this expectation is the idea of reparameterization. Okay. Once you do that, this entire loss function becomes tractable. What about the second KL term? The second KL term, see, we have assumed this to be Gaussian, we also assume PZ to be Gaussian. So, KL divergence between two Gaussian distributions is have a known closed form solution for it. Okay. So, the first term becomes differentiable through reparameterization trick. The second term becomes differentiable because of the distributional assumption that we have made. So, the entire elbow now becomes differentiable. The way to do it is, now take an x which is your data point, pass it through the encoder, get a mu and sigma, okay, and then sample a z from this particular distribution, pass it through the decoder, get an x, compute this first term, okay, compute the second term, and then back propagate the gradients with respect to theta, and then back propagate with respect to phi and learn them jointly. That is how a VAE is trained. Okay. The only I mean, it is trained as a normal neural network. The only difference is that the problem of differentiating through a sampling step is overcome by using the idea of transforming a one random variable to the other, which is called the reparameterization trick. Okay. I am discussing at a surface level and not going into the detail deliberately, because this is a sort of trailer to my next course, and we'll go into the mathematical details of all of this when we start the generative modeling course. Okay. Did you get the like overall idea of what's happening here? So, it's basically elbow optimization, okay, for the case where the posterior of the latent variable given data is not tractable. What you do is you represent the variational distribution and the data conditional using two neural networks, okay, and then optimize the elbow using reparameterization trick. So, once the neural network is trained, how do you use it during inference? You can use VAE in two ways. You can use, because it is a latent variable model, you can use it for the embedding extraction, and you can use it for generation as well. Okay. Now, how do you use it for the embedding extraction? Take the encoder, the trained encoder, get a data point, pass it through it, get a mu and sigma. Either you can use mu itself as the feature for x, right. Did you note this as well? In this formulation, for every data point x, we have a different distribution on the latent space. So, we get as many distribution on the latent space as there are data points. So, now post training, if you give one data point as an input to the encoder, you get the mean and variance. Either you can use the mean itself as the embedding for the data point, or you use that mean and variance, sample a particular point from Q of z given x, because you know what the distribution is, and use that as an embedding. That is also a possibility. People do both. So, this is how you extract embeddings from a VAE. In fact, improvisations of this is what is called as VQ VAE and so on, vector quantized VAE, which we will discuss later. Is that in fact the go to latent variable models for images today are VQ VAEs. Those are the state of the art embedding extractors for images. You know what people do? They train a VQ VAE on images and get embeddings. Now, build a generative model on embeddings, not on the data space. For instance, you construct a diffusion model on the latent space of the data that is obtained by some VAE, okay. Then sample from the latent space of that particular generative model, from the generative model. Final data is rendered by passing that latent space through the initial decoder so that the user can consume it. Do you understand what the thing is? Build a latent variable model first on given data, okay. Use the encoder to extract embeddings. Now build a generative model on top of embeddings. Why do you want to do that? Is because data space is pretty large. You do not want to, I mean, building generative models on top of it is too compute heavy, right. So you build a generative model on the latent space. Now finally you sample from the latent space, so you cannot display the latent space, right. So you pass that generated sample through the initial decoder and then that is what you display. In fact, when you ask all these modern day LLMs to generate pictures these days, this is exactly what is happening. So they do not sample in the data space. What they are doing is they have an encoder, customized encoder decoder model, okay, which is pre-computed. A diffusion model mostly is trained on the latent space, that is imposed by a encoder decoder model, and when you give a prompt, the generation is happening in the latent space, and then what is being displayed is that latent variable being passed through the decoder of the initial encoder decoder model that was there. Make sense, right. So that is how you use the encoder of an VAE. How do you use the decoder? Of course I already told you, right. You can use the decoder as a generative model or a sampler, where you take a sample from Q of z given x, pass it through the decoder, you get a sample that is not there in the data set. Got it? Diffusion model is simply another sampler which we will not be discussing now, right. No, it is an entire model, right. So you, just like we looked at GANs and VAEs, right, diffusion model is another class of samplers, okay, which is the state of the art today. So today the state of the art for image generation is diffusion models.